Hi, my name is Summer, and this is my lab report on oscillations. The purpose of this lab is to examine the motion of a spring mass system where the mass swings in an arc while oscillating on the spring. This enables us to predict the motion over time and compare the predicted and observed motion of the mass in both x and y directions. We can then plot the energy changes computed from the model. This concept can be explained by Newton's second law of motion, which states that the net force is equal to the product of mass and change in velocity over time, or simply known as mass times acceleration. The velocity update formula is used to predict new velocity, and the position update formula is used to predict the new position to predict the motion of an object. The spring force is a non-constant force that can be found using the spring constant, relaxed length of spring, and the stretched or compressed length of the spring. The gravitational force on the mass is the product of the mass and the gravitational constant in the negative y direction. The period of oscillation formula is used to calculate the spring constant for the system. The energy principle demonstrates that the change in the total system energy must be equal to all of the energy transfers with the surroundings. Thus, it is the sum of kinetic energy, gravitational potential energy, and the spring potential energy of the spring mass system. However, for this system, there are no interactions that transfer energy. If we ignore small interactions in this experiment, the attachment point is fixed and does not undergo any displacement, so there is no work being done, and there is no energy transfer. Therefore, the change in total energy of the system should be zero. The results for this experiment is that the predicted and observed motion of the mass are similar in both the x and y directions, but it is more similar in the x direction. The change in total energy, which is the sum of the change in kinetic energy, change in gravitational potential energy, and the change in spring potential energy, is equal to zero. In this experiment, the system is the mass, spring, and earth, and the surroundings is nothing because there are no interactions that transfer energy to and from the surroundings, if we neglect small effects like air resistance. Here is a tracker analysis video showing the motion of a spring mass system over time. We will be looking at both the x and y direction, so the ball moves up and down as well as oscillating to the right and left. This is why the x and y positions over time are oscillating as the object moves up and down or left and right in the graph shown to the right. The initial conditions include the mass of the system, observation start time delta t, and the system's initial position and velocity. The initial position was obtained from the tracker video, and the initial velocity was 0, 0, 0 because the system starts from rest. I chose delta t to be 1 over 210. The spring constant and relaxed length were obtained from the pre-lecture videos using these formulas. The total energy of the system is the sum of the kinetic energy, gravitational potential energy, and the spring potential energy all together. The equations for each type of energy are incorporated into the code as shown here. The gravitational force is the force due to gravity, or negative mg, in the y direction. The spring force is calculated with the spring constant, displacement relative to relaxed length, and the unit vector L hat. The net force is the sum of the gravitational force and the spring force. To apply Newton's second law, I modified the code for the object's velocity and position to create the predicted position plots that can be compared to the observed model. The spring was updated using the previous equations to find the vector L. Once again, I applied the energy principle and found the changes in energy for kinetic, gravitational potential, and spring potential energies using the corresponding equations, where changes in energy is equal to the final energy minus initial energy for each type of energy. Here are the results for the computational model. The object moves in an oscillating motion, and the graph produced shows the changes in kinetic energy, gravitational potential energy, spring potential energy, and the total energy. The graph on the left shows the changes in energies over time, and the graphs on the right show the change in position of both x and y positions over time. The change in kinetic energy is shown in blue, which oscillates and is smaller in magnitude than the others. The change in gravitational potential energy is shown in red, and the change in spring potential energy is shown in green. These two are opposite to each other, meaning as the change in spring potential energy increases, the change in gravitational potential energy decreases. The total change in energy is shown by the orange line, which is 0. The x position versus time graph shows that the model is a pretty accurate representation of the experiment because the graphs are very similar to each other. However, the y position versus time graph, even though it's similar, it shows some variations at the high and low peaks. Since the model is over-predicting the y position compared to the experiment, this could indicate other forces or interactions, such as air resistance, which can influence the y position of the system. Some sources of error would be ignoring other forces, such as air resistance, in the computational model. Additionally, there may have been some error when marking the center of mass of the object in tracker, altering the position data. Using the change in energy versus time graph, the sum of the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy is equal to 0, which is indicated by the orange line. The energy principle is satisfied because the change in total energy of the system is 0. The spring potential energy is equal in value and opposite in sign to the gravitational potential energy, which means it is 0, and the change in kinetic energy is also 0, as the blue line oscillates in positive direction and then negative direction within each time interval. The period of oscillation from the x position data was calculated to be 1.652 seconds, and the period of oscillation from the y position data was calculated to be 1.671 seconds. Since these periods are very similar to each other, having a difference of only 0.019 seconds, it means that the system behaves somewhat uniformly in both x and y directions.